So the aim of this podcast is to calculate line integrals of vector fields and to discuss when the answers depend upon the path and when they are not dependent upon the path. And I'm going to do this through an example in 2 dimensions, and the field that we're going to be integrating over has a parameter here that I'm calling kappa, and the paths that we're going to consider start and end at these points. One of them is a straight line and one of them is an arc of a circle. So let's start off by writing down the general formula for line integral of a vector field parameterized. Write down the parameterizations for each of these paths and calculate the line integrals. So for the path C1, we have a straight line, and our parameterization of a straight line is going to be r, the position vector on the straight line, as a function of our parameter that I'm choosing to call t, and it's going to start at the initial point, which I can call r sub I. So in this case, this is our initial point. And then as the parameter increases, we're going to go along the line, and the line is in the direction of this point minus this point. So what I have to do is to say I'm going to add to it the parameter, which I'm calling t, times rf minus ri. And rf and ri are just notations for the position vector of the initial point here and the final point here. So this is our parameterization. T goes from 0. At 0 this vanishes, and it's at the position vector is the initial point, all the way up to 1, and when t is 1 we have ri plus rf minus ri, so the ri's cancel and our position vector is at the final point here. So this is our parameterization, and t is going to be between 0 and 1. And ri is this point here, and its position vector is just going to be j. And r sub f, the final point, has position vector I, just the unit vector in this direction. So we can put all of that together, and what that tells us, it's easy to check, is that the position vector on the straight line as a function of our parameter t is ti plus 1 minus t j. And we can at the very least make a minimal check. When t is 0, this vanishes. This is 1 then times j. That's exactly correct. That's our initial position. And when t is 1, that vanishes, and we have that our position vector is 1 times I, and that is indeed the final point. So this is our parameter. This then tells us, if we differentiate it with respect to the parameter, that the derivative of the position vector with respect to t is I times 1 minus 1 times j. So I get that by differentiating this with respect to t. This just gives us I, this gives us minus 1 times j, so that's that. So now let's recall the key formula, which is that the integral of a line vector, the line integral of a vector field over some path called C1 in this case, is the integral over the parameter from its starting to its final value of f scalar product with the derivative of the position vector with respect to the parameterization, and then integrated with respect to the parameterization. So now we are ready to calculate this line integral over C1, because we know what this is. and we can recast f, which is given here, in terms of the parameter t. So to do that, we go back to our expression here for r, and this is the value of x in terms of our parameter. So x in terms of the parameter is t. This is the coefficient of the unit vector in the y direction, so this is y. So y in terms of t is 1 minus t. So with that we can rewrite f. So this tells us that f as a function of t is kappa times x, and x is t, times y, which is 1 minus t, so that's in the I direction, plus, and then it's x squared, but x is t, so it's just t squared j. So now all we need to do is take the scalar product of this with this, that's going to give us a scalar, and we integrate it with respect to t from the lowest value to the final value of the parameterization, and in our case that's t integrated from 0 to 1. So what we need to calculate is that this integral over c1 f dr, this scalar product, is the integral from 0 to 1 of kappa times t, so that's kappa times x times y, and that's 1 minus t, and then the next term is going to be plus x squared, but this dots into this, it gives us a minus sign, so we get minus, and it's x squared, but x is t, so it's t squared integrated with respect to t. And now if we just tidy this up a little bit before we calculate it, what we find that we get is the integral from 0 to 1, and now we have kappa times t, where we've said this is t times 1. The other term gives us a t squared, but there's a t squared here as well. So if we put those two together, what we find is we have minus kappa plus 1 t squared dt. And these are two straightforward integrals. This gives a half, this is going to give a third, and then we just put these things together and tidy it up, and I'll just make a bit more room and write down the result that we get. So what we obtain is that our line integral over this path C1 is going to be kappa over 2 minus kappa plus 1 all times a third, and if we put that over a common denominator of 6, we're going to find that we have 3 kappa over 6 minus 2 kappa over 6. That's going to give us overall a factor of kappa, and then here we have minus 1/3, which is minus 2/6. So what we get is kappa minus 2 all over 6, and that is our answer for the first path. So what I want to do now is on the next slide to calculate the line integral of the same vector field, again with the parameter kappa, from this point to this point again, but now not following this path but following this path. And what we're going to see is that generally we get a different answer, but there is going to be a value of the parameter for which they agree, and we are going to be able to understand why, and calculate it then that value of the parameter in a completely different way. So let's stop now and repeat this calculation, but for this path here. So for the second path, which is an arc of a circle as drawn here, starting at the same point as before and finishing at the same point as before, we recognize that the radius of the circle is 1, so we can parameterize the circle as something like a sine times I plus cosine times j, and it could be the other way around, but remember, when our parameter starts at, say, 0, we want to be here, and therefore we want here to have a cosine of 0. Cosine of 0 is 1, sine of 0 would vanish. That starts there. And when t gets to pi over 2, we want the sine of pi over 2, which is 1 here, so that we're here, and the cosine of pi over 2 is 0, so we are indeed at this point. So this is our parameterization, and t goes from 0 to pi over 2, and then we can differentiate this with respect to our parameter t, and this just gives us this result immediately. Derivative of sine is cosine, derivative of cosine is minus sine. So let's now write out what f is. F, the vector field that we're going to integrate over, is kappa xy I plus x squared j. And we can read off what x is from here and what y is from here. So xy is sine of t times cos of t, and x squared is sine squared of t. So we have kappa sine of t cos of t I plus sine squared of t j. So we've rewritten our vector field in terms of the parameter t, and now we have to take the scalar product of this and this, so that's going to give this times this, and then we add to it, but there's a minus sign from here, this times this. So what we see is that the scalar product of f dot the derivative of r with respect to the parameter is going to be kappa sine of t, and then it's cos times cos, so it's cos squared t, and then careful with the minus sign, and then it is sine cubed of t, and that is our scalar product. Now when we look at this, we realize we could integrate this by inspection. This is the derivative of cosine, so something like cos cubed, if you differentiate it, will give us this. And here we have sine times sine squared. The power here is odd, and that means we can write this as sine times 1 minus cos squared. So let's do exactly that, and what we get is kappa sine of t cos squared of t minus sine of t times sine squared, which I'm going to write as 1 minus cos squared of t. And now when we look at this, we see that here we've got two terms, sine of t times 1, so sine of t, that'll be easy to integrate. And this term, sine times cos squared, is exactly of this form. Overall there's a plus sign, so we can just put it together here. So what we get is kappa plus 1 times sine of t cos squared of t minus sine of t. So this tells us that our line integral over our path C2 here of f along this path is going to be the integral over our parameter 0 to pi over 2, and then it is kappa plus 1 sine of t cos squared of t minus sine of t. So that's just exactly what we had here, integrated with respect to our parameter t. So this term here, kappa plus 1, is just a constant multiplying it, and if you say that you had cos cubed, if you differentiate cos cubed, you bring a 3 down, reduce the power by 1 to cos squared, and then multiply following the chain rule by the derivative of cosine, which gives us minus sine. So we would get minus 3 times sine of t cos squared t. We don't want the minus 3, so we're going to put a factor of minus a third in front of it. And to cut a long story short, what that tells us is we have minus 1/3 kappa plus 1 cos cubed t. And if you pause now, as it were, and just differentiate this, you can see that that reduces to this, so the integral has been carried out correctly. And this is to be evaluated between 0 and pi over 2, but we've also got this integral here, and this is a very easy integral. It's plus the cosine of t. If you differentiate that, that gives you minus sine of t. So this is all between 0 and pi over 2. Now, at the upper limit, we're going to have the cosine of pi over 2, which vanishes here and here, so all of this vanishes up at the upper limit. At the lower limit, you're going to have the cosine of 0, which is 1, cosine of 0, which is 1, and there will be an additional minus sign from being at the upper limit. So what we obtain is minus brackets minus kappa plus 1 all over 3. So that's this term multiplied by 1 cubed plus 1. So now we can work out what this is, and what we obtain is kappa minus 2 all over 3, where I've borne in mind that there was this minus sign outside multiplying everything. So this is our answer for the second path, and we notice that this is not the same as for the line integral over the first path that I called C1. But if we look at this, we see that this result vanishes when kappa is equal to 2. And if we look at the first result, we also had that that vanishes when kappa is equal to 2. So for the special case, kappa is equal to 2 here, we get the same result for both paths. And what I want to do for the remainder of this video is to understand why that's the case and calculate the result using a different method. So let's move on to the next slide and do that. So what we've seen so far in this podcast is we've calculated line integrals over this vector field over two paths that started and ended at the same position, and although we generally obtained different results, we saw that the results were the same when the parameter kappa here was 2. And therefore we wonder whether this might be because when kappa is equal to 2, this vector field is a conservative vector field. So question, is f of x and y when kappa is equal to 2, so it's 2xyi plus x squared j, a conservative vector field? And what that means is we are asking ourselves, can we write f in the form of minus the gradient of a scalar that I'm going to call phi? And the choice of a minus sign here is purely a convention I'm going to use. If you don't use a minus sign here, it just means you've absorbed a minus sign into the definition of phi, and it doesn't really change anything. You've just got to be careful about minus signs, of course. So you might be able, on looking at this, to immediately work out what it is, but I'm going to do it slowly and see how we get it. So what we need is the following. Is the gradient of phi, or minus the gradient of phi, equal to 2xyi plus x squared j, and that means minus d phi dx I minus d phi dy j. So this gradient, this is what it means, putting the minus sign everywhere. And can we write that in this way? Well, if it's to be the case, this must be minus the derivative of phi with respect to x, and this must be minus the derivative of phi with respect to y. So we have to be able to integrate them both and see that we get the same phi. So let's do that. So we integrate, and from our first result, that this must be minus the derivative of phi with respect to x, we get that minus phi is going to be the integral of 2xy with respect to x, and that's going to be x squared, and then over 2, but that will cancel with the 2 here, so we're just going to get x squared y, and then that could be plus a constant, and the constant could be anything that doesn't depend upon x, so I'll call it g of y. So g of y involves things that depend purely upon y and things that are purely constants. Similarly, if we look at this and integrate it with respect to y, what we obtain is minus phi is going to be the integral of x squared with respect to y, so that's x squared y, plus terms that do not depend upon y but could depend upon x, so I'll call that h of x. And now what we want to do is we want to compare these two and combine this information about phi. So minus phi is x squared times y, plus terms that might depend on y but don't depend upon x, but minus phi is also x squared y, so the same thing, that's good, plus terms that might depend upon x but don't depend upon y. So the only solution is that g of y and h of x might just be a constant, so it's something that depends on neither x nor y. So what we see is that minus phi is x squared y plus a constant c. And what we're going to do now is to use this to calculate the line integral for an arbitrary path. And before I do that, I'm going to make some room. So what we want to do now is to use the general result for a line integral over some path, c1, c2, whatever path it is, it doesn't matter, here. And if we have this for a conservative vector field, so it's minus grad of phi dotted into dr, this is equal to minus phi evaluated at the end of the path plus phi evaluated at the beginning of the path. And if in your definition here you don't have a minus sign there, then you would just have different minus signs. That would be plus and that would be minus here and here. So this shows you, this equation here, that there is no path dependence, it just depends upon the endpoints, and this is true for a conservative vector field when we can write the vector field as essentially the gradient or minus the gradient of a scalar potential. So now, what is the potential? potential is written here. There is a constant c, but that will cancel. Here you would have minus c, and here you would have plus c, so they will cancel. We don't need to worry about it. And at the final point, we have that x is 1 and y is 0. So x squared y becomes 1 squared times 0, so the potential minus phi is 0. So we have minus 0 plus, and now at the initial point we have x is 0 and y is 1. And when x is 0 we have 0 squared, which is 0 times 1, so we're also going to get plus 0. So therefore what we obtain is that our integral, the line integral over the conservative vector field in this example, vanishes, and the line integral over a conservative vector field is generally independent of the details of the path. It depends upon the endpoints, and in particular it depends upon the values of the potential at the finishing and starting point. So this is exactly the result we obtained for both paths when kappa was equal to 2, and now we have understood it, and we also know that if we had taken some totally different path connecting these 2 points, for this potential where we have kappa is equal to 2 in the vector field, it would still always vanish. And if you wish to, what you could do, for example, would be you could say, supposing I was to go from here along the circle in the anti-clockwise form from here to here, you could calculate that and check again that it vanishes. And with that, I will stop this podcast.